Good evening, everyone. This is the live session for Polymer Reaction Engineering noc23 ch29 uh, sample problem discussion session. My name is Rohan Jadhav. We will be discussing some sample problems in this session so that you will be able to solve the assignment problems for this week. So this week we'll be going over radical polymerization uh, and how its aspects are important in understanding the rate equations for the polymer reactions. In the first question, we can see that radical chain polymerization can be divided into three steps, which are initiation, propagation, and termination. Among these steps, the rate determining step in almost all of the polymerization reactions is we have initiation, propagation, and termination. So in radical chain polymerization, you know that propagation reaction is very detrimental to the entire polymerization process. That is because large number of monomer units are converted to high molecular weight polymer in this stage. Since initiation only begins the reaction of radical uh, radical, and the real polymerization starts in the propagation process where the large molecular weight products are formed. So propagation is the rate determining step in almost all of the radical chain polymerization reactions. Uh, for most of the compounds to be thermally initiated, it must be having a bond dissociation energy of. So for covalent bonds, the bond dissociation energy limit or the bond breaking or bond breakage of the covalent bond is about 100 to 170 kilojoule per mole uh, through thermal initiation reaction. And since this is very narrow, this limits the use of compounds having activation energy above or below this limit. So that's why the correct answer would be 100 to 170 kilojoule per mole. Of course, we have studied it from the activation energy concept that once you reach the threshold, threshold energy and activation energy we have achieved, uh, the reaction proceeds. Reaction proceeds in that manner. So the covalent bond breakage occurs through thermal initiation, occurs at 100 to 170 kilojoule per mole inverse. Moving on, we have the rate of polymerization reaction does not depend upon the selection of initiator species. However, initiators are need to be selected on basis of operating temperature. The rate of polymerization reaction does not depend upon the selection of the initiator species, but it depends on that is because the number of monomers which is used in the initiation process is very less when compared to the chain propagation. So that is the exact reason why the RI term, which is rate of polymerization during the initiation process, can be neglected. But initiators are needed to be selected on the basis of operating temperature. Yes, because as we saw in the last session that the operating temperature is very detrimental for the initiation of the polymerization reaction. The very first assumption, which the very first assumption need to be taken for determining a rate kinetic expression for radical chain polymerization rate is that the rate constant for initiation should be independent of the radical size of the radicals. So this is actually incorrect because when we go back to the calculation of the rate constant for the radical chain polymerization reaction, the very first assumption is that the rate constant for propagation and termination are independent of the size of the radicals, not the initiation. So that's why this statement is false. So in that case, Kp and your Kp terms are dependent upon the size of the radicals, size of the radical. And initiation is not dependent upon the size of the radicals. So that's why this assumption is false. Moving on, we have three statements here, and we have to find out which one is the correct. So, reaction inhibitors are added to monomers to avoid the premature thermal polymerization during transportation, storage, and delivery. The second statement is benzoquinone is an example of reaction inhibitor, and third one is impurities present in the monomer can also act as a reaction inhibitor. So, you can see that reaction inhibitors are added to monomers to avoid premature thermal polymerization during transportation, storage, and delivery. Yes, reaction inhibitors are added to the monomers so that monomers don't undergo any spontaneous reaction if there is any thermal property changes because of external thermal agents, which might increase or decrease the temperature. So, because of that, reaction inhibitors are added to the monomers to avoid any kind of premature thermal polymerization process. Next, so this statement is true. Moving on to the next statement, benzoquinone is an example of a reaction inhibitor. Yes, benzoquinone is widely used to stop radical polymerization of vinyl derivatives, where benzoquinone traps the reactive intermediate radicals and changes it into non-reactive radicals by stabilizing it through resonance effect. So that's why benzoquinone is an example of reaction inhibitor. Next, we have impurities present in the monomer can also act as reaction inhibitor. So the impurities present in the monomer can either act as a reaction inhibitor or might not act as a reaction inhibitor. That's why that statement is a bit ambiguous because impurities might also aid the monomer uh, in propagating the reaction quickly. So that's why statements one and statement two are correct with almost utmost certainty. Moving on to the next question, we have in order to carry out a spectroscopic analysis of a chain of a polymer. If the polymer contains strong IR absorbers, then NIR will be a better alternative than IR spectroscopy to obtain the linear response of the spectrum. NIR stands for the near infrared spectroscopy, where we are dealing with so in case when we are dealing with strong IR absorbers such as for example water, it is actually helpful in keeping the linear uh, response of the spectrum linear. This is because overlapping of the components can be somewhat resolved in the NIR spectroscopy, and spectra of individual components are additive in nature in NIR spectra. So that's why it will be more easily resolved. So yes, it is true that in presence of strong IR absorbers, NIR will produce better results than your standard IR spectroscopy. Moving on to the next question. Solvents are the liquid substance that do not dissolve the given component of solution during precipitation polymer reaction. Uh, in precipitation polymer reaction, what happens is that when the polymer chain growth reaches a uh, certain limit, the products precipitate out of the solvents. So solvents are liquid substances that do not dissolve the given component of a solution. Saying this statement would be incorrect because the polymer was found will precipitate out of the solvent since it is not able to dissolve it anymore. So that's why the statement is false. Moving on to the next question. We have in case of high viscosity polymers, the size exclusion chromatography cannot be used due to the clogging of reactor by viscous polymer fluids. Uh, in case of size exclusion chromatography, what happens is the packing material which is used inside the columns, right? Uh, they are formed of small uh, gel permeation beads, and these beads are quite porous in nature. So because of their porosity, what happens is that the 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 high viscosity polymers and polymeric fluids which might have broad distribution can be separated or classified through these pores, and because of that standard distribution can be obtained in case of high viscosity polymers. So GPC or SEC is suitable for polymers containing large and small size molecules, and it, it is very much applicable for the radical polymerization process. So the statement that this process cannot be used due to clogging of the reactor is false. Moving on to the next question. At very high concentrations, at very high concentrations of initiators, the order of rate of radical polymerization reaction, RP, its dependency on the initiator concentration, I, can be found to be less than half. The reason can be attributed to, uh, we have three options here: resonance stabilization, impurities present in the monomer, and cage factor. So, since the concentration of initiators and the order of rate of radical polymerization, its dependency on the initiator concentration can be found to be less than half. So what happens is that uh, amongst these impurities present in the monomer, impurities are small in concentration. So a high initiator concentration can be used to offset the impurities present in the monomer. So that won't be dependent on it. And as far as resonance stabilization goes, resonance stabilization's dependency on initiator concentration is not significant. So in that case, cage factor, where radicals are formed from decomposition of an initiator molecule, uh, which are surrounded by a cage consisting of solvent or monomer molecules, is what occurs in a cage effect. So within the cage, recombination of radicals can take place, which can deactivate the reaction. So deactivation of the reaction would be a very undesirable process. That's why the cage efficiency is defined, where the ratio of rate constant for cage combination to the sum of the rate constants for all cage processes can be defined as cage efficiency. So that's why cage factor is a very detrimental process in which can explain the reason why the why at very high concentration of initiators the order of radical polymerization dependency and initiator concentration is found to be less than half. Moving on to the next one, 11th question. The selection of an initiator depends upon the operating conditions such as reaction temperature and the rate of the homolytic cleavage. As discussed in the previous question, yes, the selection of initiator is dependent upon the operating conditions such as reaction temperature and the rate of the homolytic cleavage, because the rate of polymerization is dependent on the initiator species, and initiation is critical, and activation energy barrier plays an important role during selection of initiator compounds. So that's since activation energy comes into picture, the reaction temperature will be a big factor in controlling it, as well as the type of initiation which we are looking at, like the homolytic cleavage. Uh, that's why initiation is critical, and in that case, the selection of the initiator will be dependent upon the operating conditions such as reaction temperature and rate of homolytic cleavage. So this statement is true. I hope that by looking at these sample problems, you might be able to solve the assignments for this week. And uh, and for the next week, we'll be discussing more about radical polymerization and other types of polymerization processes. Thank you.